So it says Twitter is an online news and social networking service, okay, on which users post and interact with limited size messages known as tweets. Design the Twitter timeline and search. Okay, I see. So we have to design the timeline and search. Okay. So when you say search, what exactly does the search mean here? Are we searching for the tweets or are we searching for people or like what?
Like I guess it says about searching tweets. I guess.
Searching fields. Okay. To search means that we are going to search for fields. What fields do we mean here? Like search for words in tweets, like tweets.
Or we can say like we will search for people. Like that will be more precise.
Okay, search for tweets, people. Makes sense. Okay, for now, these are the two main things. Okay, and timeline. What it basically contains is the posts from people the user follows. Okay, and it can also have news. So, are we also supporting news for the purpose of timeline?
I guess like
Huh? Sorry.
news like we can like
Okay, we support news as well. Okay, fine. So uh, we have the people. Uh, how are the people using our Twitter? Like, do they use their web browser, basically the desktop, or do they also have mobile apps?
So
Um,
for this case, we will consider for web only, so,
okay,
because it's not given anywhere. So we will consider for
okay,
later. We can consider it for other like
sure.
other phones also,
Okay,
like other
so
devices also. Yeah.
okay, now we have a web interface, and the client they use say desktop client to access our Twitter system. Okay, and so in the timeline, how would we show the tweets or the news? So let's say there are two, I mean, there are two friends of mine or two people whom I follow. They have posted something at time A, at time, let's say 7 a.m., and someone had posted at 8 a.m. So should I show 8 a.m. Tweet first and then 7 a.m.? That is the reverse
Like
order.
most recent one we will show first,
Okay.
then yeah.
Most recent post first. So that means this is reverse chronological order. Okay. Uh, And how do we want to support the searching, like each character, or should we wait for each word? Um, like,
uh,
so
Basic
what?
search that is supported like that will be like by each character, I guess.
No, I
Basic
mean,
search.
in Google, if we type something after each character, it shows us
Yeah,
the
then suggestions,
suggestion.
suggestions.
So, do we want to show something like that, or is it like once the user types the entire word,
No.
then
That like we will follow the traditional because nothing is given as such, so we'll follow the traditional method.
the traditional method, which is
Like the which Google follows. In Twitter also, if you see like it will follow the same way.
okay, okay, type ahead system for search. Okay, uh, like uh, so what is the scale of our systems that we are looking at? Is it like we have just started, or we are looking for actual scale of Twitter, like billions of users? Um, so
Okay, so like we will go for the like actual user
okay, so
actual number.
can I assume there are like 10 million daily active users?
Yeah.
Okay, and there are like let's say 2 tweets per day uh, by a user, and mm, um, and there are like 10 people that uh, who just uh, read. So basically, what I mean is that on an average, a person just have around 2 tweets per day, and the number of reads to writes is in a ratio of um, maybe 10 is to uh, 5 is to 1. So like 5 people read, but only 1 people posts. Okay. Uh, okay. Uh, Fine. And uh, what are the attributes that we want from our system? One is that it should be scalable. Um, the other thing is that it should be mm, it should be available. I mean, in case of fault, it should not go down, and it should have um, um, scalability around, and it should be reliable. I mean, if there is something stored in our system, we should be able to retrieve it. There should be no data loss. Okay. Yeah, I think I have all the requirements that I wanted. So let's start with the functional requirements from our Twitter. Um, so basically, our Twitter should support two APIs, which is like post tweet, and then so one more thing, in the tweets, are we just having the text messages, or is it like text, image, video,
No,
etc.?
no, just text only. Like,
Okay. Tweets consists of text only for now. Okay, so there should be a post tweet API that should take some text, um, and user ID, like who is making this tweet,
yeah,
and there should be one API that should be supported as um, get timeline for a given user ID, and one more thing is search. Um, let's say we use some prefix, and it will show us the top K suggestions. Okay. Here I have written the functional requirements in form of functional APIs. Um, we could transform them into REST APIs if needed. Um, but yeah, let's go ahead. So these are the basic functional requirements that I want from my system. The non-functional requirements are like the system should be scalable, so that if there are more users, it should not like it should be able to handle that as well. The system should be reliable. I mean, there should not be any data loss. It should be available in case of partition. Um, um, uh, I mean, the system should still function, and um, so the data should also be, I mean, so far let's go with these. mm, okay, now let's see how we can design the system. Um, so there are two things. um, there are two components to this system. One is the data ingestion and other is the data query. So basically, there should be a way for the data to enter into our system, and then we would do some form of processing, and then there should be another way to get the data out of the system.
yeah.
So let me draw this up. Let me share a link with you. Just a second. Mm, just a second. Uh, I'm just checking how to share this. Mm,
And like, what will be the network architecture for this? Like,
yes, I'm just coming.
yeah, okay.
Just a second. So can you open this link?
Yeah, yeah, sure.
Are you able to access it?
Like, so I'm not able to see the diagram.
Like, are you able to access this? I
Yeah,
mean,
yeah. This drive I can access, but it is giving me some XML code. Like
XML
after,
code.
yeah, like not XML, some similar to that, like some other code.
Mm, I mean, I have drawn a box. Can you see that? Synchronous share. You're not able to see this.
Actually,
It's the same link. Uh,
like, I'm getting this things. I guess I don't have like that proper application to do this.
okay, never mind. Let me draw it here only then. Okay, so there should be a data ingestion flow, and then there should be a data query flow. Um, so let's say what happens is that there is a user who accesses it, our system to our client, and then they will make a request to our service. So our service, what it will do is, let's what service is this? Uh, mm, so there is a tweet service. Well, let me call it post service. So basically, its job is only to take the tweets from the user and store it into some data store, and then there will be a query service, or we can say timeline service, um, using which the user would be able to see the timeline. And now, since we also want to have the query system, what we can do is, uh, in the same vein, we can also have something. Similarly, there would be a search service. What it would do is, again, the user client uses the search service to access uh, the search results. So this is a very simple high-level diagram of what our system will do. So I will walk through this once again. So we have our post tweet, right? So I mean, in the user client will, user will make a post tweet request. It will go to the post service, and post service will insert into the data store, and all such tweets and posts are inserted into our data store, and then we would have our timeline service, which when a new user or whoever user wants to open like whenever they open their app or they open the website and login, a request would be made to the timeline service, um, which will basically compute all the requests and put them in a reverse chronological order, and return it back to the user. And similarly, if user makes a service, search in the search bar, that would come to the search service, and search service would return the top case suggestions based on the prefix that user has entered, and it will be shown to the user. And this search service also interacts with the data store to know, it computes what are the top case suggestions. So let's talk about the data model here. What do we actually need from our databases? What data do we need? So definitely there should be a user table that will consist of user ID, um, and um, um, as far as the data base is concerned, um, I mean, uh, we can, like, it depends upon how we model our data. So and uh,
Basic structure you can give, like
yeah.
you can tell the foreign keys and those things.
So I was like we have two options now. Mostly, like, in fact, we have three options. Either we use our relational databases, MySQL,
Uh,
PostgreSQL, or we use the NoSQL like Cassandra, DynamoDB, etc. Or we use the graph database when we have such kind of connections, or we can use them in conjunction as well. So two or more databases, depending on what suits what kind of data. So let's assume that. So far, I believe our data can be modeled as a relational database. Um,
yeah,
So let's begin with that. So we have a user, then user will have a user ID and all the related details like name, uh, address, cell number, etc., etc. Um, and then we should have a tweets table or posts table that will consist of tweet ID, and that will consist of the user who posted it, and uh, when was it posted. So like created at, last modified at, uh, fields like these. So whichever user posted this will have the in the user ID, and also that tweet basically, which is our text in this case. Um, and then um, uh, we will have a follower table, which basically tells us who is following whom. So there is like follow e, um, and then there will be like follower, and both of these are like user IDs. Follower is also a user ID, follow is also a user ID. So like if a follows b and c, in our table we would have something like, um, followee is a and the person whom he is following is b, and followee is a again and person whom it's following is c. So our table will look like this, and that way we would be able to find out how many uh, persons this a person particular, I mean, the person is following. Okay, so this is what our data would look like. And if we need to make a query, then we can, I mean, um, we can combine user and tweet using this user ID, which is like primary in the user, I mean, user table, it's primary key, and in tweets it will be a foreign key. And similarly, in the follower table, um, we will have both followee and follower as the foreign key, and it
Like
will tell us.
uh,
Hmm?
we have created this follower table. So don't
Hmm.
you think like it will be like the data A will be redundant? So we can separate the tables to avoid this redundancy. So it will be a normalization part. So later we can.
Hmm. I mean, so A is the followee and B is the follower, correct? There would be redundancy. This is what, uh, like, I mean, in normalization, this is what it happens. We can't have multi-valued attribute. I mean, there was one way through which I could have done that if this was like no SQL kind of system, that A follows B and C, but I
Uh,
can't have B and C. We can't have multi-valued attribute in relational databases, right?
yeah.
So I need to separate it out, even though it looks redundant. But the beauty is that relational databases are, um, I mean, we can index it up. We can set the indexing based on these, so it will be like able to query very fast whoever are the followers. So this is what these three tables would look like, and we can create a timeline based on this only. Um, uh, so, I mean, from the following, mm, so we would make a query like select tweets from tweets. Uh, uh, Okay, so select tweets and user, where tweets dot tweet ID equals to users dot user ID, and um, mm, mm, I mean, I'll have to query this follower table. Um, so who are the followers of the given user? Um, where followee, uh, join. mm, Let this be joined with follower, where tweets, where users dot user id equals to follow e id, and instead of the user I get from follower dot um, follower. Okay, yep. So using this query we'll be able to get all the I mean followers of the given person, and then we would be able to construct all the tweets, I mean timeline, and then store it again in a, let's say, in a timeline table. um, so timeline table will consist of what, user id, and the timeline basically. So what posts? I mean, in fact, this timeline will consist of all the tweets ID that it needs to show, and um, um, yeah. So this is how we can construct a timeline. And for the search, we would use a distributed trie. Um, so are you aware of the trie data structure?
Not much. I have heard of it, and one or two questions I have done in DS.
Okay, like so trie data structure is it's like an n-ary tree. I mean, each child can have multiple, I mean, each node can have multiple children, and we just compute this just like we construct a normal binary tree. But at each node we will store how many top k suggestions are there. In our case, let's say if we are going to have top 5 suggestions for search, we will be able to store that. So let's say there is b a, I mean, there is a node whose first character is B, then it's one of its child is A, then its child is T. So at T, I mean the word is bat. From BAT again there could be a word BATH. So at let's say I have something like this. Uh, So this is how our tree looks like. So at this place, we can store that bat and bill are the two top suggestions. And if user just types B, we will show him that bat and bill are the two top most important post tweets. If it types BA, then we should show him something like um, maybe um, bath and bat are the two top most that starts with BA, and similarly others. So we can use a distributed trie for the searching and store this in a hash table uh, so that we can make a query. And in order to reduce the latency, because searching is latency sensitive, we can use Reddish cache or memcached depending on whichever is easier for us to implement. I mean use. So yeah, that's my high level design. But there are a few things. So like let's move into the non-functional requirements of these. So user is making a query to post service, and there are a lot of users. I mean, if we have 10 million daily active users, I can compute what's the read and write request per second. So if we have 10 million daily active users and each user makes like what we have discussed, tweet two tweets per day. So so there are 10 million users and 2 tweets per day, so that's like 20 million tweets per day. So this is what around so if I divide it by 10 to the power 5, which basically is like 86,400, I have rounded it off. I mean 24 into 60 into 60 will give us for each second. So if I round this off, this becomes um, uh, it's like 200 m divided by 10 to the power 6, yeah, 1 m. So this becomes 200 writes per second. So this is the write uh, I mean 200 writes per second on an average, and peak can be around 400 rps. And reads are how many? So we had what reads are like 5 times. So reads are like 1k rps, 1000 rps. So if each server I mean handles around like so the thing is, if we are having a post service, a single instance won't be able to handle it. So we need multiple instances, right? So we can have n number of these, and now if we have n number of these, we need a load balancer or API gateway here. So either we use a load balancer or API gateway, depending on what kind of architecture we are having. So in the microservices-based architecture, we use API gateway. Normally, we use load balancers, and behind that, we have n number of post service, and then we would have our data store, and then we would have similarly n times, uh, I mean n number of timeline services, and n number of search services, and again those would be like front-ended with let's say load balancer. In short, I would call it LB. Okay. This is I wish I could have drawn this. This looks bad. Okay.
So this is like I'm not able to get these things, but it's still like I will try to understand.
What exactly are you not able to?
Like it is beyond my scope, but I will.
Okay. Yeah. So this is what
No,
I
no,
mean,
like I'm getting the thing what you are saying, like, but I'm not like far of these things.
yeah, I mean, it's fine. You'll get hang of it. So this is what our system would look like. So we can have a load balancer that does like load. I mean, we can have multiple services behind it, and it just does a round robin scheduling and sends the request to those services, and those are in turn like they use the data store to put the data and create timeline and all. And in order to make those requests faster, we can have caches. So timeline definitely would help with the cache. um, and search service also, it needs a cache because these are very latency sensitive, and doing the computation at read time for timeline and search will take a lot of time, so definitely these should be cached. The post service doesn't need a cache, it just takes the data and puts in the data store. Now there could be one problem, that data store is busy, so post service will like it might take some time. I mean, so the data store could be very busy, and post service is just waiting for the data store to take in the data. So in order, so this is a consumer, like producer consumer problem. So in this case what we can do is we can have a queue, like if to decouple these. So this is like message queue. Any sort of messaging queue or message broker will work here, Apache Kafka or RabbitMQ or any form of queues. So that once it's I mean the data is written to this message queue, which will be backed by the I mean it's it will be a reliable service which doesn't lose data. And then like there could be another service that puts out data into the data store. So we could have a task runner uh, at this stage to pull out the data from message queue and insert into the data store. So yeah, now this looks good to me. Okay, yeah, I'm done. um, and the caching, like we can have a LRU based cache or a time based cache. Like for a timeline, I would suggest we can have a time based cache, that after this time we should refresh it. I mean, it should be paused. And when so they, okay, like there could be problems in the data store also. So like since we have so many writes coming, we have almost 200 requests per second, right? For the write request. So a data store won't be, a single instance of data store won't be able to handle it. So we need to partition our data. So to partition the data, we can use the key range based partitioning. Like so we can say that all the A to K goes to first node, then L to Z goes to second node, and then we can have one one leader and two follower nodes to persist the data. Okay, so this accounts for replication, and then we have partitioning. If the data goes beyond this number, then we can further partition this data and keep on more nodes. Yeah, so that's it. Um,
Okay.
like, do you have any questions? Are you able to hear me?
Hello. Am I audible to you?
Yeah, yeah. Yes. Now you're audible.
Okay. So, so any enhancement that we can make, uh,
Enhancement to what?
in this architecture that you explained, this like non-functional one.
Okay, non-functional ones. So we had scalability. We had, I mean, in order to handle the more number of users, scalability. Let's say what we have. We have like one load balancer. We can have two load balancers or n number of load balancers, or we can say a cluster of load balancers handling all the data. Then we already have multiple instances of post service, so that is already scalable. We have a distribute. We can use a distributed message queue again to handle the high traffic. Then data store, we have already partitioned it, we have replicated it, so that's good. The cache, we can use a distributed cache for scalability. So distributed cache like Redis can run on multiple machines to store like gigabytes of data or even petabytes of data, depending on how much data do we need. And then for the timeline service, there are already n number of services, and again we have load balancers, so that it's already taken care of. So scalability is there. How about reliability? Okay, so reliability is like data should not be lost. So we already have message queue that's backed by the by the file system. So I mean, anything when it gets inserted to a queue, it's also is written to the file system, so that if it goes down, then it would be able to restore from the last point checkpoint. And then we already have a data store with one leader and two follower nodes. I mean, this configuration makes sense because we do have a lot more reads. So the reads can go to either leader or the follower, and writes will go to the leader, and then it will go to the follower nodes. It may happen that a leader receives it before the follower can catch up with it. So what we can do is we can say that there is one leader, one uh, async follower, and one sync follower node, which means that as soon as a leader gets a write request, it will also send it to a sync follower. And once these two write to their own copies, they will tell that okay, write is done, and then later on the other write can go to the sync follower. And in case the leader dies, there will be heartbeat among them. So I mean, so there would be a control plane for these, which would ensure that there is always a leader. In case we don't have a leader, it will promote one of the followers to become the leader, and also raise an alarm that one node is down, so that DevOps can look into it. Um, then we have uh, availability. So availability is like, um, in case of distributed system, if uh, one copy of it is down, then again we should have the. I mean, the system should be up and running. So here the problem can come with the data store. So in our database, um, we have the availability, because if even if the leader is down, there is always a follower. So um, so I mean, there is one sync follower. So if the leader is down, so we can always get the latest write from the sync follower, and we won't lose any data. And sync follower would be promoted to the leader meantime. We have a message queue as well, which makes the system available. Like I mean, the point of using that was it would decouple the producer and the consumer, so that would also work. It would also handle the spiky traffic. So in case like in case suddenly, like there is some breaking event or breaking news, breaking post, so suddenly a lot of tweets or retweets would start coming into our data store. So instead of bombarding it with that, we can have it in the message queue, and task runner would later on pick from the message queue and insert into our data store. So one thing that can happen is like there could be a hot partition, that is there is one post that is getting a lot of writes. So what we can do is we can add another uh, like another partition for that hot node. Uh, I mean, there could be a node for hot partition that will handle all the tweets related to it. And since I mean, ideally, what we should do is whenever a new tweet comes, we would insert into the Twitter timeline, right? And update the user that okay, here there is a new tweet for you by your by the people whom you follow. But in case of hard partition, if we do that, there could be a lot of people just for that particular tweet. So let's say Prime Minister did some post, right, and there are a lot of people following it. So instead of updating all the people who follow the prime minister and updating their timeline, we can not do that instantaneously, and in fact let it. Um, I mean, when the user makes a request to that timeline, then we would add it at that moment instead of sending a notification.